welcome back to this course. This is the third session of our course. Last session, we learned how to develop a new numerical method for solving delay differential equation. Now, we want to assess the numerical method to derive the numerical solution of a state-dependent and time-dependent delay differential equation. We consider three different choices of the set of base function, and for each example, we present the absolute error to compare the results. We choose eta base function as a base. We know about that. We choose Legend polynomial and also sine and cosine function as a base. In this example, we have a pantograph delay differential equation. We want to investigate this delay differential equation. X, the derivative of x equals to g of t, x of t minus and x dot t minus t theta to theta. Here, these parts are our delay term, and they can be pantograph delay differential equation, state dependent and time dependent. In the first example, we have pantograph delay differential equation. As you see here, we have t half, and delay term is qt. Here q is half, and g, here we have g is this function. The exact solution of this pantograph delay differential equation equals to t times sine hyperbolic of t. As you see, it is a hyperbolic function. We choose 4 terms of the base function for eta base function, legend polynomial, and sine and cosine function. And in this table, we have absolute error for this example by using eta base function as a base, legend polynomial, and trigonometric function. You can see when we use eta base function, the absolute error for this example is about 10 to the minus 16. But about legend polynomials and trigonometric function, we have the absolute error almost 10 to the minus 2. And you can see the eta base function for the delay differential equation that has exact solution as hyperbolic function are act very better than legend polynomial and trigonometric polynomial. Also, in this example, for reaching the absolute error of order 10 to the minus 16, the CPU time consuming by the software in legend polynomial was almost 42 times greater than in the eta base function case. And this accuracy was not achieved when we use sine and cosine function. So you can see the efficiency of our numerical method. Another example, we have g of t equals to this function. Here we have multi-pantograph delay differential equation. We have one delay here, x of t half, and one of here, t divided by 4, t quarter. For this, and the exact solution equals to e to the minus t times cosine of t. The absolute error for this function, for eta-based function and trigonometric function, is in this table. For different case of n, n3, 7, and 11, we can compare this result. For n equals 3, we have the absolute error about 10 to the minus 2, and here we have 10 to the minus 3. But when n increase, you can see that the absolute error for eta-based function is less than from the trigonometric function, and it's about 10 to the minus 10. Also, the CPU time consuming by the eta-based function for this example is here, and you can see it's about 10 to the minus 3 seconds. Another example is time-dependent delay differential equation. g of t equals to this. Here, theta of t is ln of t plus 1 function. And the exact solution here is sine hyperbolic of t. In this example, the absolute error shown in this table for n equals 3. For eta-based function, the absolute error is equals to 10 to the minus 16. But for Legendre and trigonometric polynomial, we have a function, we have the absolute error about 10 to the minus 2. So we can see eta-based functions are suitable for deriving the approximation solution of an equation that have trigonometric or hyperbolic exact solution. In this section, I want to investigate integral equation. You can see here a Volterra and Ferret-Holm integral differential equation. In this equation, p of t is a vector function of order n. G of t is a vector function of order n, and k1 and k2 are kernel function, and they are a vector function 2, and lambda 1 and lambda 2 are constant vector, because we have vector here. The best approximation of rho I is equals to H transpose of T times di. Here, H transpose is the base vector, and this is eta-based function. So we can write P of t here, H hat of t d hat. Here, d hat is n times 1 vector, and H hat is a identity matrix of order n times n, Kronecker product, H transpose t, and H hat here is n times n matrix. By replacing these equations in our main problem, we can write this equation. Now, for this term and this term, Volterra and Ferret-Holm integral, we use Gauss-Legendre numerical integration for evaluating this integral. So we can write this equation. We use Gauss-Legendre numerical integration for this part and for this part. In this equation, Wi are the weight of Gauss-Legendre, and here and nu I are weight, are node of Gauss-Legendre. So we can write this equation. Now we collocate this equation at the node of Chebyshev polynomials. We can have a n times n nonlinear equation which can be solved for the elements of the hat by using the Newton's iterative method. Here I have some example for you. First, we suppose that we have a first-Holm integral and an integral differential equation, and K2 equals to k of t and s times e to the root of s. Here, k is a t times s, and the exact solution is cosine of t. So we have trigonometric function as an exact solution. The absolute error for this example by using eta-based function, Legendre polynomials, and trigonometric function shown in this table. And you can see for this example, when we have the exact solution cosine of t, eta-based function and trigonometric function are near to each other, but Legendre polynomial is less than, it has the absolute error more than these two, eta-based function and trigonometric function. Another example that we want to see is when we K2 equals to k of t and s root 2 of s. Here, k of t and s equals to ts. We choose for first term of the base for all three different choices of this function, and you can see here absolute error by using the eta-based function equals to about 10 to the minus 11. But for Legendre and trigonometric function, it's about 10 to the minus 4. So for this example, when we have the exact solution equals to t times sine hyperbolic of t, you can see the absolute error of eta-based function is more or less than from Legendre polynomials and trigonometric function. Okay. In this section, I want to talk about orthogonal polynomials. We know that orthogonal polynomials play an important role in spectral method and approximation theory, and they have a lot of important properties that in this section we want to investigate some important properties of them. Answer in the break. Yeah. Okay. The family of orthogonal polynomials constitute a basis of the Hilbert space L2 with the standard inner product given by this equation. Inner product of f and g equals to integral from a to the b f of x times g of x times w of x. Here w is our weight function. These orthogonal polynomials satisfy many important properties, among which we highlight some of them. First, the polynomial Pn of x is of degree exactly equals to n for all n bigger than or equals to 0. The 0 of Pn of x are simple and they are located in the interval of a and b. Also, we have the following orthogonality properties for orthogonal polynomial. Integral from a to b, this product equals to Cn Kronecker delta of order n and m. We can write this integral as this integral. We can write integral a to b, x to the m times Pn of x times w of x b0 for m less than n. The weight function here, w of x, is bigger than or equals to because if it will be 0, it is equals to 0. It's bigger than 0 for all x in interval a and b. Another property, it's a very important property, is that a sequence of orthogonal polynomials satisfy in this three-term recurrence relation. X times Pn of x equals to, you can see here we have Pn plus 1, Pn minus 1. In this equation, an and bn can be obtained from these relations, these equations. Also, p minus 1 equals to 0 and p0 of x equals to 1. It is a very important property of orthogonal polynomials. Another interesting property of orthogonal polynomials is that the derivative of orthogonal polynomial also form orthogonal polynomial set. Here we have orthogonal polynomials satisfy a second order linear differential equation of the Astor-Liouville type. You can see we have a second order differential equation, and where here p of x is a polynomial of degree less than or equals to q of x is a linear polynomial, and lambda n is independent of x. We have an important equation here, Pearson equation. From this equation, that is famous as a Pearson equation, we can find the weight function. It is a first order differential equation, and by using this, we can obtain the weight function. For example, the weight function of Hermite polynomials, Laguerre polynomials, Jacobi polynomials, and other orthogonal polynomials. And the last important properties that I want to say, it's Rodrigues-type formula of orthogonal polynomials is defined as this equation. Yn of x equals to this when n derivative of wx, the weight function, times p to the n of x divided by this is yn of x. Here p of x is polynomial in x and independent of n, and here an is not dependent on x. From from this formula, we can obtain a lot of information about orthogonal polynomials. In this section, I want to investigate some important properties of some important classic orthogonal polynomials, such as Hermite polynomial, Lager polynomial, Jacobi, and also I want to investigate some properties of Bessel function too. Okay, let's start with Hermite polynomials. The Hermite polynomials orthogonal with respect to these weight function e to the minus x2 and named for the French mathematician Charles Hermite. Hermite polynomials can be represented by these series expansion, and it is important for us, denoted by these hn of x, and they have this series expansion. Here, this part is the integer part of n half. The first theorem is the Hermite polynomials are defined by these generating function, and now I want to show it to you. Okay, we say that Hermite polynomials have this series expansion. Now we want to show that the generating function of Hermite polynomials is this function. Series n from 0 to infinity t to the n divided by n factorial hn of x. By using the Taylor series, we can write here the Taylor series of this exponential function. Series are from 0 to infinity to tx to the r divided by r factorial times s from 0 to infinity. For this, we can write it r and s from 0 to infinity. I want to write this in this is similar to this series, so we can write minus 1 to the s 2x 2 times x to the r, and here we have t2 to the s tr, so we have t2s plus r divided by r factorial s factorial. Now we want to pick out the coefficient of Tn. I want to know about the coefficient of Tn. The coefficient of Tn, it should be hn of x divided by n factorial, and I want to show it to you. For fixed value of S, the coefficient of Tn can be obtained by taking, it's clear, by taking 2s plus r equals to n. 2s plus r equals to n. So here we have, we say that for a fixed value of s, from here we have r equals to n minus 2s. By taking 2s plus r equal to n, the coefficient of Tn can be is for a fixed value of s. Minus 1 to the s 2x. Here we have r equals to n minus 2s. N minus 2s n minus 2s factorial s factorial. Here we have the coefficient of Tn for a fixed value of s. So the total coefficient of Tn can be obtained by summing on all allowed value of s. So we have the total coefficient of Tn series from, I want to talk about this, minus 1 to the s 2x n minus 2s divided by s factorial. Okay, look at this. We know that r is bigger than 0. So here we have n half is bigger than or equals to s. So we know that s goes from 0. When n is even, it's even. It's n, the upper one is n divided by 2. When is odd, it will be n minus 1 divided by 2. So we can write in general, s goes from 0 to integer part of n half. And you know that from this, look at this, they are similar too, except we have here s from 0 to n. Only we don't have this term. So we can write it 1 divided by n factorial, and we know that if this series expansion is about hn of x. So we have the generating function of Hn of Hermite polynomials can be obtained from this. In the next part, we can see that these generating functions help us to find and to know about the orthogonality properties of Hermite function and to obtain the Rodrigues formula for Hermite polynomials. Okay. We have another theorem here. It is very important for us. The orthogonality property of Hermite polynomials of order n is integral minus infinity to infinity. So Hermite polynomials are orthogonal on this interval. Hn of x times e to the minus x2. So the weight function for Hermite polynomials is a to the minus x2. And the orthogonality property of these polynomials is this equation. Now we want to show it to you. Okay. From the generating function, we know that we have e to the 2 times t times x minus t2 is this has this series expansion. We can write here e to the 2sx minus s2 equals to m from 0. I want to show that orthogonality. M from 0 to infinity, s to the m factorial, hn of x. By multiplying these two equations, we can write times e to sx minus s2 equals to series from n to infinity. Here we can write n and m equals to 0 to infinity tn. And it is better, yeah. Listen, no, it's okay. Now, by multiplying a weight function e to the minus x2 on both sides of the equation, and then by integration from minus infinity to infinity dx, we have this equation. Now we know that the coefficient of Tn times s to m divided by this is this integral for the series expansion of this integral. So you can see I want to find this term. of this integral. E to the minus x2 e to the 2tx minus t2 times e to sx minus s2 dx. But we know that we can write this integral in this form. It's e to the minus x2 plus 2tx plus 2sx dx. And also we can write it e to the minus x minus t plus s to the 2 plus t plus s to the 2 dx. With a simple computation, you can see it is equals to this, and it is equals to e to the 2s t integral minus infinity to infinity e to the minus x minus t plus s dx. By changing the variable, we can obtain e to the minus u to du, and we know that it is the square root of p. By using the Taylor series of these exponential functions, we can write it Sn Tn divided by n factorial. Okay, so we find that this series expansion equals to this series expansion. So we find that if n is different from m, so we have this integral equal 0. And when n equals m, we have tn, sn, n factorial, n factorial. So we have here n factorial times n factorial. Yeah, I forget. I think I should e to the here we have t2st, so here we have 2n. Okay, so we have for n equals m, we have the coefficient of the integral minus infinity to infinity hm times e to the minus x2 is equal to the square root of p times n factorial times 2n factorial. So we have integral minus infinity hn of x equals to we can write is when n to n, and show that these orthogonality properties for Hermite polynomials on interval minus infinity to infinity. Another theorem that is important for us is the three-term recurrence relation for Hermite polynomials is hn plus 1 of x equals to 2x hn minus 2n hn minus 1. By using the series expansion of Hermite polynomials, we can obtain this easily. And here we have another important formula, Rodrigues formula for Hermite polynomials. It is hn of x equals to this term, the n derivative of e to the minus x2 times e to the x2 times minus 1 to the n equals to Hermite polynomials. In this section, I want to show it to you. Okay. By using the generating function, and you can see that the generating function is very important for us for Rodrigues formula for obtaining the orthogonality of polynomials. By using the generating function, of Hermite polynomials, also by using the Taylor's theorem. Taylor's theorem is that f of t has this series expansion n from 0 to infinity n derivative of f respect to t at t equals 0 times t to the n divided by n factorial. We want to show this theorem, the Rodrigues formula for Hermite polynomials, by using the generating function of Hermite polynomials and Taylor's theorem and this. Okay, from the generating function of Hermite polynomials, we know that hn of x equals to series from n from 0 to infinity hn of x t to the n factorial is equals to e to the 2x minus t2. It's generating function that we prove that. So by using this and this, we can we find here we have ft, and here we have the n derivative of this function with respect to tn should be hn. So we have this function the n partial differential equation, the n partial differential of this equation respect to tn equals to Hermite polynomials of x at t equals to 0. we can write this e to the x2 minus x minus t to the t at t equals to 0. It's equal to this. So we can write it. We want the derivative of this function to the t. So here we can write e to the x2 e to the minus x minus t at t0. Also, we have a property here. N partial derivative of fx minus t respect to tn equals to minus 1 to the n partial derivative of fx minus t to the x to n. So by using this property, we can write n derivative to the x respect to xn. So we change it from t to x. So we can substitute t equals to 0 in this equation. And here we have dn e2 minus x 2, and we compilate the proof. We obtain this Rodrigues formula for Hermite polynomials. Okay. In this section, I want to talk about another important orthogonal polynomials, Laguerre polynomials. Laguerre polynomials, named for the French mathematician Laguerre, Edmond Laguerre, and denote by ln of x and have these series expansion. ln of x equals to this summation. Similar to Hermite polynomial, we have some important properties of Laguerre polynomial. Laguerre polynomial has the generating function as this e to the minus x times t divided by 1 minus t divided by this is this summation. And now we want to prove it. And we know that we can obtain important properties such as orthogonality properties of Laguerre polynomials, the Rodrigues formula of them by using these property. Okay, we want to show that divided by also we know that Laguerre polynomials has the series expansion r n factorial n minus r factorial to the 2 x r. Okay, Again, by using the Taylor series, we can write r from 0 to infinity minus x t to the r divided 1 minus t to the r divided by r factorial. We can write it r plus 1. Also, from binomial theorem, we have this property: 1 divided by 1 minus t to the r plus 1 equals to series s from 0 to infinity r plus s factorial, r factorial, s factorial, t to the s. It's binomial theorem. By substituting this in this section, we can write r and s from 0 to infinity minus 1 to the r, x to the r, t to the r, and we have t to the s. So we can write t to the r plus s. R plus s, excuse me, we have here at the r minus s. Yeah. No, it's correct. R plus s factorial, r factorial, s factorial. Because we have 1 divided by this equals to this summation. So we can write, now we want to find the coefficient of Tn in this series expansion like Hermite polynomial. Tn. Here is the final equation that we obtain. Here, for a fixed value, of r, the coefficient of Tn can be obtained by taking r plus n equals to n for a fixed value of r. So here we have s equals to n minus r. So the coefficient of Tn for this fixed value of r is this, minus 1 to the r x to the r plus s equals to n. We can write n factorial divided by r factorial and s n minus r factorial. It's the coefficient of Tn for a fixed value of r. So the total coefficient of Tn can be obtained by summing on on a loved value of R. So we have the total coefficient of Tn equals to R. We can write xr n factorial divided by n minus r factorial. Yeah. And here we have s equals to n minus 1. And we know that s is bigger than 0. So we have r less than n. So in this section, we have r from 0 to n minus 1 to r n factorial xr n minus r factorial to 2. Here we have r factorial to 2. I should check it. Okay, here we have a mistake. We have r factorial, and by substituting this, we have r factorial here. So here we have r factorial to the 2. And you can see that it is logger polynomial of order n. So the generating function of logger polynomial can be obtained by using this function. And by using this generating function, we want to show the orthogonality property and the Rodrigues formula for logger polynomials. Okay, we have a 10-minute break and then we continue. The next theorem that we want to investigate about is the logger polynomial are orthogonal on the positive real line, integral 0 to infinity, and the weight function for this orthogonality properties is e to the minus x. And now we want to show it to you. Okay, from the generating function of logger polynomial, we have this. We can write also e to the minus x s divided by 1 minus s equals to series from m from 0 to infinity lm of x s to the m. By multiplying these two equations, we can write e to the minus xt times this term equals to summation n and m from 0 to infinity tn times sm ln of x lm of x. By multiplying e to the minus x on the both sides of this equation, it's the weight function, and integration from 0 to infinity is the end in the interval of orthogonality for logger polynomial. We have this equation. Okay, so we know that this integral is the coefficient of t to the n s to the m of this integral. So integral 0 to infinity ln x lmx e to the minus x. And we want to find this integral is the coefficient of Tn Sn in the expansion of this integral 0 to infinity. I can write, here we have integral respect to x. I can write 1 divided by 1 minus t times y minus s, integral 0 to infinity e to the minus x minus x times 1 plus t divided by 1 minus t plus s divided by 1 minus s dx. And it's a simple integral and can be obtained this, and it's equal to 1 divided by 1 minus st. Okay, we know that we can write this fraction in base of this summation, and from 0 to infinity s n t n. So we find that this integral will be 0 when n isn't equal to m, and it will be 1 when n equals to n. So we find that integral 0 to infinity ln of x dx equals to delta Kronecker of n and n, and we find the orthogonality properties of Laguerre polynomials. Also, we have another theorem here. The polynomials satisfy the three-term recurrence relationship. From this equation, we can find Laguerre polynomials. For example, we set n equals to 0 to 1, and we can find all of the Laguerre polynomials from this recurrence relation. And it is by using the series expansion of Laguerre polynomial, it can be obtained easily. Another theorem that we want to prove it's the Rodrigues formula for Laguerre polynomial. The Rodrigues formula for Laguerre polynomial can be obtained from this equation. The n derivative of this function times this function equals to Laguerre polynomial. And now I want to show it to you. Okay, I want to show by using Leibniz theorem for the n derivative product two function, we have n derivative of u times v respect to x to n can be obtained from this series or from 0 to n factorial n minus r factorial the n minus r derivative r of u times r. It's the Leibniz theorem for n derivative of product of two functions. By using this, for this equation, we can write the respect to x and e times e to the minus x is equal r from 0 to n factorial n minus r factorial. Here we have the n minus r of u. Suppose that is u and it is v x n times dr v e to the minus x ex r. So here we have n factorial divided by. We know that it will be n factorial, n factorial x to the r divided by r factorial times minus 1 e to the x. So look at this. We have here this summation and times e to the x divided by n factorial, we can find the series expansion of Laguerre polynomials. So we prove this theorem too, and we obtain the Rodrigues formula of Laguerre polynomials. Okay. Another classic orthogonal polynomials is Jacobi polynomial. Jacobi polynomials are defined by these hypergeometric function. We talked about hypergeometric function. Its order of 2 and 1, and its element is here. And we know that here it's a Puch-Hammer's symbol. The Jacobi polynomial can be presented by this series expansion, and also we can write them like this series expansion too. And the Jacobi polynomial has these orthogonality properties respect to this wave function 1 minus x to the alpha times 1 plus x to the beta is the wave function on interval -1 to 1, and its integral equals to this term. Okay, here I want to show two special Jacobi polynomial, Legend polynomial and Chebyshev polynomial. First, I want to talk about Chebyshev polynomial and then about Legend polynomial. The Chebyshev polynomials of first kind, because they have some kind, we have some kind of Chebyshev polynomial, first kind, second kind, and other, can be obtained by using Jacobi polynomials when alpha equals to beta equals to -12. So when we set in Jacobi polynomials, alpha and beta equal to minus half, we can obtain Chebyshev polynomials. And we use Chebyshev polynomials for base function for solving differential equation and another differential equation, for example, fractional differential equation, very much. The orthogonality properties of Chebyshev polynomials can be obtained from this equation. They are orthogonal on interval -1 to 1 respect to it is right, it's not true, it's the square root of 1 divided by square root of 1 minus x2. I should correct it. Tn of x, Tm of x, and it is very simple to show it. We know that Chebyshev polynomial can be obtained from this cosine of n theta. Here, theta is cosine inverse of x. So we can write it cosine n cosine inverse of x. Now, we want to find this integral -1 to 1 Tn of x, Tm of x, and the wave function is 1 divided by a square root of 1 minus x2, that we correct there, dx. Okay. By using the change of variable x equals to cosine of theta, we have integral for x equals -1, we have p, and for 1 we have 0 Tn of cosine of theta, Tm cosine of theta times 1 minus cosine of, it will be sine theta, and for dx we have minus sine of theta. So we can omit this and we can write it integral 0 to p, and we know that Tn of cosine of theta, it will be cosine of n cosine inverse of cosine. So we have here cosine of n theta, and for this we have cosine m theta d theta. And from the property of the trigonometric function, we know that it is 0 when n is not equal to m. It is p when p half when n equals to m to 0, and it will p. So we know that Chebyshev polynomials are orthogonal respect to this weight function. Also, in this section, I want to show you how to obtain the weight function of Chebyshev polynomials too. I said that by using this formula, we can find the weight function of Chebyshev polynomials. From the second order ordinary differential equation of Chebyshev polynomials, that they are the exact solution of them, we can find that Px is 1 minus x2. So we have 1 minus x2 times w of x equals to, and qx is minus x. We have these differential equation, and it is simple to show that minus 2x times wx plus derivative of w is equal to minus x w of x. So here we have 1 minus x2. Derivative of w is equals to x times wx, and we can write w prime of x divided by w of x equals to x divided by this, by integration. On both sides of this equation, we have ln of w of x equals to minus half ln of 1 minus x2, and it is equals to ln 1 divided by the square root of this. So we find that w of x is, so by using this property we can find the weight function for Laguerre polynomial, Hermite polynomial, Chebyshev and Legendre polynomial, and all of classic orthogonal polynomials. Here it is better, it was better that I give you the differential equation of Chebyshev polynomials. You can search the net and obtain it easily. I don't have it with me. Okay, now I'm going to talk about another special Jacobi polynomials, Legendre polynomials. Legendre polynomials obtained from Jacobi polynomials by setting alpha equals to beta equals to 0. And they are hypergeometric function of order 2 and 1 by these elements. And also they satisfy in this three-term recurrence relation. You can see that here we have Pn plus 1, Pn minus 1. It's one of the property of orthogonal polynomials. Okay. Also, we know that Legendre polynomials are the solution of this differential equation. For example, for Legendre polynomial, here we have px, and here we have q of x, and so you can find the weight function of polynomials by using this equation easily, and it's 1. Now we want to show that the orthogonality property of Legendre polynomials satisfy in this integral, and I want to show it to you. Okay. Here we said that Legendre polynomials are the solution of this differential equation, and here I want to use this equation. Suppose that Pn of x and Pn of x satisfy Legends equation. So we have 1 minus x2 minus 2x plus n times n plus 1 of Pn of x equal 0. Also we have the second derivative of Pm respect to x, 2 minus 2x derivative of Pm plus equal 0. Now, by multiplying this equation by Pm and this equation by Pn, and then by substituting this equation, from this equation we have Pm 1 minus x2 T2 Pn of x minus 2x. We have here, okay, before I multiplying that, it is better than to write this and then we can write this equation as this equation, and after that we do, okay, we can write it the derivative of this term look at this, the derivative of this term, it will be minus 2x dpn, we have this term, 1 minus x2, the second derivative of pn to x2, this term, plus n plus 1, pn equals to 0, and dpn equals to 0. Now, by multiplying this equation by Pn and this equation by Pn, and then by substituting this equation minus this equation, we can obtain Pm, the derivative of minus Pn plus n times n plus 1 minus m times n plus 1 Pn Pm equals to 0. Now, by integration from this equation on interval -1 to 1, we have this. But we know that we can write the derivative of this term respect to x equals to the derivative of Pm respect to x times 1 minus x2 derivative of Pn respect to x minus 2x Pm minus Bpm yeah, okay, minus Pm dx Bpm respect to x. We know that we can write it. It's simple, and it's the property of derivative of function. So for this part, here we have this part. We can write it is in base of these terms. So we have minus dpm dx 1 minus x2 dpn dx, and for this we have minus dx pn dpm dx plus dpn dx 1 minus x2 dpm dx equals to this term m times m plus 1 minus n times n plus 1 pnx dx. In this equation, we can see terms can be omitted, and we have here the derivative of this part respect to x minus the derivative of this part respect to x can be obtained as Pm 1 minus x2 dPn dx minus Pn times 1 minus x2 dPm dx. X change from minus 1 to 1 equals to m times m plus 1 minus n times n plus 1 integral minus 1 to 1 pnx pmx dx. You see that this term can be 0 and this term is 0 in 1 and minus 1. So for n is not equal to m, we have minus 1 to 1, integral minus 1 to 1 is 0. So it remains to prove that integral minus 1 pnx pmx dx equals to 2 divided by 2n plus 1. Now we show that for n is not equal to m, is not m, we have 0. And now for this theorem, we want to show that for n equals to m, we have this integral as 2 divided by 2n plus 1. In this section, we want to show some important properties of orthogonal polynomials, and then we want to use these properties for deriving the approximation solution of some differential equation, such as fractional differential equation, and it is necessary to know about them. Okay. And for legendary polynomial and Chebyshev polynomial, I don't speak about the generating function of them, but they can be obtained easily, and like the Hermite polynomial and Laguerre polynomial, you can try to obtain them. The generating function of Legendre polynomial is this function, 1 divided by 1 minus 2x plus t2. X. We can write equals to Tn of x, and from 0 to infinity to the 2. Also, by integration from minus 1 to 1 on both sides of the equation, we have this and from 0 to infinity Tn plus m Pn of x Pm of x dx. Also, we know that this integral equals to plus t2 from minus 1 to 1, and it can be obtained as this. And here we have from the last part, we know that for this case, we have this integral equals to 0. So here it should be n equals to m. So we have here infinity t to the 2n integral minus 1 to 1 pn of x pm of x dx. And by using the expansion, the series expansion of ln of 1 minus t and ln 1 plus t, we can write this term as two series from n0 to infinity t to n plus 1. By using the series expansion of each of these equations. So we can see here the coefficient of t to the 2n is integral minus 1 to 1 pn is equals to 2 divided by 2n plus 1. So for n equals to m, we have this term and we complete the proof. Okay, I talk about some properties of some classic orthogonal polynomials such as Legendre, Chebyshev, and Hermite and polynomial and Laguerre polynomials. And next session, I want to talk about Bessel functions as a orthogonal function. And then I want to use these properties to obtain the approximation of fractional differential equation. So next session, I should give you some preliminary definition of fractional calculus 2. I finish what I was going to talk about this session. If you have any comment or question, please let me know.